Hello everyone, welcome back to AICE Physics stuff. So I didn't finish up this from before. It's literally going to be about waves, so Unit 12 of the AICE Physics. I know it's past paper 2, but this is more of a educational approach to waves. So we'll start where we left off. So in this part B, a stationary wave is formed on a stretched string between two fixed points A and B. The variation of the displacement y of particles on a string with distance x along the string for the wave time t is equal to 0 is shown on figure 5.1. So we have a string right here. So the wave has a period of 20 milliseconds and a wavelength of 1.2 meters. Okay. The maximum amplitude of the particles is 5 millimeters. So up to here for each one, right? On figure 5.1, draw a line to represent the position of the string at 5 milliseconds. So initially we're given that everything is at 0. So the three possible waves is going to be like this, right? And then after a while, this goes down, like this goes up, and it becomes like that. But they still go in the same direction. So this is still going down, this is still going up. And then you have a wave like this. And then it reaches a maximum, and then it starts going the other way, like that. And then we're back to where we started. Yeah. So basically we start from either position like 2 or position 4, basically. And we can choose which one to start with. It doesn't really matter for this one because they don't specify exactly where. I know recently for the what is it? The 2-1 for the May-June series 2026. They just told you to write a possible wavelength. So we know the amplitude and what it can look like. So we're gonna draw a sinusoidal wave. So something like this, right? But we have to figure out exactly the amplitude as well as the wavelength. So the wavelength is 1.2 meters. So we'll have an up and down, or a crest and a trough, I think, at 1.24. So around here, I think, right? 1.2 meters, I think. Yeah, this is 1.2 because this is 1.5, right? And there's 10 in between. So it should be the fourth square. And our amplitude is 5, so we can know that. So since this is 1.2, we go half of it to get the second hump. So this is like what? 1, 2, 3, 4, 20 squares plus 4, so I need 12 squares. So around here. So we go up, down at this area, down, up, and we repeat. This should be around 2.4, right? Yes, this is 2.4, so it's actually exactly going to be 2. So we're going to go up, down, and then we end at B. So this is a possible configuration. The other possible configuration is the same thing, but just inverted. So we go down, up, down, up, down. So that's another possible, but I don't think you can draw both of it because you only need one line. So now we state the phase difference between the string at 0.4, which is 8 squares, and 0.8, which is 16 squares. I think it's, wait, 10, 5, 1, so it's here. So we have 0.4 meters and 0.8 meters at a total of 1.2 meters. So if we think about this like in wavelengths, it's going to be 0.40 meters divided by 1.20 meters. So this is going to be a wavelength and a third. And on the other hand, we have two wavelengths on a third for 0.80 meters over 1.2 meters. And we have two wavelengths over 3. So we have a phase difference of wavelength over 3, which is around 120 degrees. And the unit, I guess degrees. Okay, so I fact checked the answer for this one, and it actually says it's 180 degrees. So I'm gonna try and explain that why that's correct. So the idea is that okay, let's look at the top one. So if we have 0.4 up here and then 0.8 is down here, for example, these two here, these two particles here, since this is a stationary wave, you think about it in like antiphases and phases basically. So essentially, if they're on the same side of the node, or if they're on opposite sides of the node, then they're going to be like 180 apart. Otherwise, they're going to be 0 degrees apart. Yeah. So in this case, it's going to be 180 degrees. If it was a traveling wave, where there aren't like nodes and antinodes, then it would be 120 degrees. Or you did like where you do the wavelength over 3 and then the two wavelength over 3 because of the 0.4 meters and the 0.80 meters. But since it's a stationary wave, we have to consider whether or not it's in phase or not in respect to nodes. So since they're on opposite sides of the node, like between the node, then it's going to be 180. Yeah, because they're the same distance away from the node of 0.6 meters here in the middle. So they're exactly 180 degrees. So, and then finally we have to state and explain the change in kinetic energy of the particle and an antinode between t equals 0 and t equals 5.0 milliseconds. Okay, so for this one, this isn't really that intuitive, but if you think about it, it does make sense. So initially at t equals 0, we do have kinetic energy. And at t is equal to 5.0 milliseconds, we don't have kinetic energy. This is mainly because for t is equal to 0, we're kind of just like in a straight line, right? We're kind of in a straight line, but we're not in equilibrium where it's just a straight line. We're either going to be moving up or going to be moving down. So there's a certain velocity associated with that, and thus we have kinetic energy. As for t is equal to 5.0 milliseconds, if we have a wave like this, technically it is not moving at this instant of time, simply because we're reaching our maximas, right? And if you've done calc, if you reach a maxima, our slope is 0. So we're gonna have no velocity, and then our kinetic energy is gonna become 0. But I should stress that this is an instantaneous time. So it's only in this exact time where we have 0 kinetic energy. Because if you go like 1 millisecond above or below, we're still going to be moving and there is a kinetic energy. But simply because it's the maximum, we have 0 kinetic energy. All right, CRO. Okay, so a signal generator is connected to 2 loudspeakers as shown. A microphone M is connected at Y plates. At the cathode of the CRO detects the intensity of the sound along the line of ABC. The distance LA and L2A are equal. The time base of the CRO is switched off. Oh, I see. The traces on the CRO when M is at A, then at B, and then at C are shown on figure 2.2, 2.3, and 2.4, respectively. So for each of these traces, 1.0 represents 5.0 millivolts on the vertical scale. Explain why coherent waves are produced by the loudspeakers. Okay, so these waves are coherent because they have, I should write this in a different color. They have constant phase difference. So they form a coherent waves from the both two. So use the principle of superposition to explain the traces shown at M at A. So at A, we have a vertical here, amplitude, and it's in the middle. So if you're seeing these diagrams, it's going to be something like that. And this is also going to be like that. Sorry, my diagram is so bad. But eventually it should become like that, where they both intersect at letter A. Use the principle of superposition. At A, both waves are at maximum, creating the amplitude, the maximum amplitude at that point. As for B, they cancel out. So one wave reaches maximum while the other reaches wait, I think they both reach minimum actually. Yeah, they actually both reach minimum. Both reach minimum. So it's something like this, where they're both, this is like A, this is B, and this is C. Both reach minimum. So total displacement is 0. And as for A, it's going to be like the same answer here, where the difference in wavelength here it's going to be a maximum. This is kind of like a diffraction grading. So this is the maximum, minimum, maximum. The sound emitted from L1 and L2 has frequency 500 Hertz. The time based on the CRO is switched on. The microphone M is placed at A. On figure 2.5, draw the trace shown on the CRO. On a vertical scale, shows this, that. Okay. Okay, so I think that the overall amplitude so 1 centimeter represents 5.0. So this is 5.0 millivolts here. So then here, if we draw on this line, we do have to do a calculation for the period. So 500 hertz is equal to 500 second negative. So then we're gonna take the reciprocal of this. We should get 0.002 seconds. And then we convert this into milliseconds, 0.2 milliseconds. So for 2 centimeters, it should be 1 wavelength. So I believe it should look something like this. Oh god. Using a stylus is so annoying. Okay, whatever. So it should be a line like this, as you go through it. Okay, so I fact checked, and my math is wrong here. So it should be 2 milliseconds because 1 millisecond is equal to 0.001 seconds, right? So it should be half a wavelength. So let me erase this. And since there's what? There's 10, right? 10 centimeters here. And each one is 0.1 times 0.1 milliseconds, right? Yep. So this is going to be one millisecond in total. So we only need half of a wavelength. So it's going to start from here. We're going to go to 5 right here and go to the end. So it should look like that instead. I apologize for the mathematical mistake. Anyway, an arrangement for producing stationary waves in air in a tube that is closed at one end is shown in figure 6.1. Loudspeaker produces sound waves of wavelength 0.68 meters. For some value of L, stationary waves are formed. Explain how stationary waves are formed in a tube. So for stationary waves, the main condition is that the wave is reflected. So we have another wave coming in the opposite direction. And then the other one is same frequency. So it's not all jumbled up, right? So the length L is adjusted between 0.2 meters and 1.0 meters, calculated to 2 values for L, for which stationary waves are formed. Okay. So I believe the formula for this is like the wavelength is going to be equal to 4 times L divided by N, where N is the odd harmonic. So N is equal to 1, 3, 5, etc. So in this case, we have a wavelength of 0.68. 0.68 meters for wavelength is equal to 4 times L over, we can say like 1. And in this case, L is equal to 0.170, which is not plausible. So we move on to the next one. And then this becomes L is equal to 0.510. And then N is equal to 5. And then L is equal to 5 over 4, so it should be 0.850 meters. And if we go on, we will eventually know that it does not work. So our only plausible values of L is going to be 0.510 and then 0.850. I'm not going to fact check that one. Hopefully my math is correct. I did that all mentally. But yeah. I should specify this is N. And then I'm just like doing a list, calculate each one. So now label the positions of the antinodes for an A and the nodes for an N for the least value. So for the least value, it's going to be something like, it's so hard to draw this precisely. So the main thing is that we actually start an antinode and then we end at a node. So it's like that. And this should be 1/4 of a total wavelength. All right. I believe that is right. And then I forgot the A and N, sorry. So this becomes A and this is an N. The diagram represents the pattern of stationary waves formed by the superposition of sound waves from the loudspeaker and the reflection of the metal. W, X, Y, Z are 4 points on the line through the center of these waves. Which statement about these stationary waves is correct? Okay. So let's go through each one. And for number A, an antinode is formed at the surface of the metal sheet. Okay, so for this one, I believe this is not correct. Because an antinode cannot form at the surface of a metal sheet. We have a metal sheet, right? If we have a metal sheet, the sound waves can't really move freely. At least that's the explanation. The explanation is like the particles can't move freely on a metal sheet. So at that point, it's going to be a node rather than an antinode. Intuitively, this should make sense because if you think about a wave or with nodes and antinodes, it's like you have relatively spaced out, and then you have a bunch of clustered, bunch of spaced out, and another bunch of clustered at each node and antinode. So wait, I drew this wrong. It's a bunch of clustered here, spaced out until you get to the next node where it's more, and then clustered again. So this is node, antinode, and it's something like that. So that's why A is incorrect. So B, a node is a quarter of a wavelength from an adjacent antinode. Yes, I believe that is correct. So if we look at this small diagram that I drew here, I drew one wavelength, and I labeled the nodes and antinodes. And we can clearly see that if we split here in the middle, half of a wavelength, we have one node and node. And we split it again, that's 1/4, and that's the distance between a node and an adjacent antinode. So this is going to be most likely the correct answer. As for C, the oscillations at X are in phase with those at Y, and clearly they are not they're actually out of phase. They have a constant phase difference of around 90, I believe. Oh, no, they have a constant of 180 degrees because it goes from antinode to antinode. As for D, the air particles oscillate perpendicular to the line of W and Z. No, they don't. These are stationary waves, so they actually do it from side to side, I believe. This is for like transverse waves, I think. So it's not these two. A musical called a bugle is a long tube with a mouthpiece at the one end. The other end is open and flared as shown. The musician maintains stationary sound waves with a node at the mouthpiece and an antinode at the other end. The lowest frequency of sound that the bugle can produce is 92 hertz, which different frequencies of sound can be produced. Okay, so we know that wavelength is proportional to the frequency multiplied, the speed. The speed is proportional to frequency multiplied by wavelength, right? And we know that velocity here is going to be a constant, and then we have to figure out which wavelength. You know what? A musician makes stationary sound waves with a node at the mouthpiece and an antinode at the other end. The lowest frequency of a sound that the bugle can produce is 92 hertz. Which different frequencies of sound can be produced by the bugle? So we should note that the wavelength, or lambda, is proportional to frequency, I believe. Right? No, I believe it is inversely. I believe it is inversely proportional. Right? So the main thing for this one is that we're actually finding waves that can fit in this type of thing, where we have a possible of this. We also have a possible of this. This is kind of a bad drawing, but we have two antinodes and two nodes. We can also have one like this, and etc. Right? And they all have to fit in this tube here. So we kind of have to take the formula from before that we used, which is like this lambda. Lambda is equal to 4L over N. But instead, since we established this relationship, it's like 1 over F is equal to 4 times L over N. And we flip it, okay, F is equal to N over 4 times L, where N is equal to 1, 3, 5, etc. And we know that our base frequency is going to be 92. So it's going to be like 92 times 3, which is 276, 92 times 5, which is 460. And then we get that our answer is actually going to be C here. Hope that makes sense. And I believe that is the end of it. I'll just say that here we have velocity is equal to lambda multiplied by frequency. So these are inversely proportional to a constant. That's how I really establish a relationship. So yeah, if you have any questions, go ahead and comment down below. I see all the notifications, so I think I'll reply within 24 hours. If not, 48 hours. But I will definitely see it. So don't be hesitant if you have any questions. You can ask me or you can use AI, you know. Um, but yeah, otherwise, like and subscribe. Thank you for your time.